Kia ora Year 12 and 13. This is the last video for today, and this is the question 3 part D and E from 2016's complex numbers paper. As usual, a merit and then an excellence question. And these are both proofy kinds of questions for general cases of complex numbers. So please, if you don't get what I'm doing here, leave me a comment on the video or send me an email and I'll try to make it go a little bit slower. But the general method here is that we've got to prove that the conjugate of uv, where u and v are complex numbers, is equal to the product of the conjugates. So we're going to start by setting up u to be a general complex number. Now, it doesn't matter what you do for this, what letters you use, but I've used x plus iy for u, and I'm going to use a plus bi for v. So straight away we know we're going to need the conjugate, so let's write out what they are. So u is equal to x minus iy, sorry, u bar, and v bar is equal to a minus bi. Right, we've got two things we've got to work out. We've got to find the conjugate of uv. So first we're just going to find uv. Right, and it's a proof question, so don't go skipping any lines. So I'm especially talking to my A-level class when I say that, right? So ax plus ayi plus bxi plus byi squared. So now we're going to group the real and the nominal bit. So we've got ax, and then byi squared is minus by, plus I times ay plus bx. So that's good. Now we need to take the conjugate of that. So uv with a bar over the whole thing will be ax minus by minus I times ay plus bx. Right, if you're just doing this with the video, make sure you've written down what we're trying to prove, because now we're going to look at what the right-hand side is. So that's my left-hand side. So u bar times v bar is equal to x minus iy times a minus bi. So that's ax minus ayi minus bx. I don't know why I'm saying all this as I go. I'm going to stop. So plus by. So again, grouping real and imaginary parts, we get ax minus by minus I times ay plus bx. But we've just shown above that that is what uv was. So we finished as required. Okay, so that's a merit question, and it's merit because it's actually pretty straightforward with exactly what you've got to do. The next question is similar in some ways, but you need to be thinking a bit harder about what it means when we're proving that something is purely imaginary. So here we've got two complex numbers, u and v, and we're given a condition about those complex numbers. We have to then show that when we've got complex numbers that satisfy this, that this thing is true. So think about what it means for a number to be purely imaginary. It means that we've got z is equal to 0 plus, say, 17i, right? So the real bit has got to work out to be 0. So that's where we're aiming to go with part E. Okay, so set it up again with let u and v equal something. So this time I'm going to let u equal a plus bi and let v equal c plus di. I'm partly doing that just to match what they've used in the marking schedule. Right, so we're given u plus v, the magnitude squared of u plus v is equal to the magnitude squared of u minus v. So first we're going to work out what are those two things. So u plus b plus v will be a plus c plus b plus d I. And u minus v will be this one, take away this one. So it's going to be a minus c plus b minus d I. Now, let's look at the magnitudes squared. So the magnitude is equal to the Pythagoras thing. So when it's squared, we're left with quite a simple expression with squares, a plus c squared plus b plus d squared. And the magnitude of u minus v squared will be this. Now going right back to the question for a minute, we're told, remember, that this is true. So we're now going to equate those two expressions. So we'll write that down, and that's equivalent to a plus c squared this. So it's pretty obvious what we have to do now. We've got to expand all of that out, and then we're going to get a whole lot of stuff simplifying out. That's the left-hand side done. And that's the right-hand side done. Now I'm going to use the highlighter to show you what's going to go. The a squareds are going to go, the d squareds are going to go, and the c squareds are going to go, and the b squareds are going to go. Right, so we're subtracting both of those from each side. So that's nice. We're left with 2ac plus 2bd is equal to negative 2ac minus 2bd. Right, let's group like terms. So we're going to add those to each side. We get 4ac plus 4bd is equal to 0. And that's the end of the road for the first part of the problem, which is to use this condition here. Now we want to show that if that's true, that this must be purely imaginary. So we're going to take u and v conjugate and multiply them together. So u times v conjugate is equal to a plus bi times c minus di. That equals ac plus cbi and so on. Right, and it's going to be plus bd for that last bit. So that equals ac plus bd plus cb minus adi. Whoops. Just let me clean this up. Right, that bracket goes there and that's there. Now, what can we say? Well, let's look back up here. We had this, 4 times ac plus 4bd equals 0, which we could also say 4 bracket ac plus bd equals 0. So that means ac plus bd equals 0. So uv bar, okay, sorry for the interruption. So uv bar is equal to 0 plus cb minus adi, which is purely imaginary. As required. Okay, so we're done. So just make sure that you're working really, really clear and easy to follow, and leave me a comment if there's any part of that that doesn't make sense, and I'll try to get back to you.